All right. Good morning, everybody. Um, so I guess just an announcement. I guess the homework is going to be pushed back, which I made that announcement on Canvas the other day. So so you have some more time to work on that. Now, I guess for the solution for the assignment is actually you have to mostly just sort of understand how to use pre and post order type traversals to mark different nodes with the camera and be able to count how many cameras you have and mark which nodes are visible based on camera placement. So really, the only hard part for the assignment is trying to decipher all that iterator and class, stuff. That's the only hard part. The actual algorithm itself is pretty simple uh, for um, for this program. So if you're wondering how to actually use a pure traversal on sort of this tree, well, in that deep copy.cpp file, I actually I gave you guys, actually it has right in there how to use a pre-order type traversal on this particular example. Now, the only difference is that the start operator for that deep copy file, it's a binary tree of integers. So I do a star operator returns integer type. So for this example, the star for iterator returns a visibility type object. So you have to use star of that iterator that points to a node, and then dot to access the camera, scene, ID, and so forth, because it returns a data field, which is that data field is going to be an entire visibility type object. So then you just use the operator on that to access a particular field. And you can, of course, you can actually reassign that field to a new value because the operator star function returns the data type by reference. So you can actually overwrite that value in main. So you actually could literally have like your R pointer or your IT iterator. You could say star IT dot scene equals true. You can even do that. And it would mark that node as a scene. It would mark it as true actually from now on. So that's kind of all there is to that. So anyway. You have until Sunday to get that done. That's going to be actually a hard deadline, so I won't push it back beyond Sunday because that's too much time at that point. But I'll have an assignment probably posted up by the weekend. It'll be using unordered maps, so it won't be anything too hard. I can talk about that a little bit next week, but nothing too bad. That one's a very simple assignment, just using an unordered map. You don't have to create your own hash map. Just use the unordered map from C++. So you don't have to create your own custom hash map, which is kind of why it's a bit easier. So anyway, I'm going to go ahead now and begin a screen share and just sort of continue from last time's lecture. So let's go ahead and screen share this. When would assignment 6B do? Well, I mean, if I post it up around this week, Thursday or Friday, then most likely it'll be due next week, Friday, but then I might as well make it due on Sunday at that point, right? So most likely next Sunday is when it would be due, most likely. And um, I may not extend that deadline because I'm not going to need to. It's not going to be anything really, really bad. So from last semester when I did that assignment, something like that, it didn't cause a giant, chaos with students. It was not so bad. So that'll be probably due next week, Sunday. And you won't need more time on that one. I mean, you should need more time because it's not really a very hard program assignment to say. It's just a nice, kind of easy way to kind of get us started with using hash maps. That's all. So just like, I went over at one example for condensing a list. Remember that? So it's going to be something along those lines, except that the value field might not be an integer. It might be like a struct type, but or actually, no, it's not. It's not going to be a struct type either. It's going to be simple integers and strings and so forth. So it won't be that bad, really. So shouldn't be anything too bad. But I'll talk about it next week, Monday. It'll be due on that following Sunday. So anyway, let's go ahead now and talk about this hash map from last time. So basically how a hash map works is going to be a very defined method of how you do a hash map. So basically over here, in this example, I create a hash map and have string and int, which basically is going to give us the key type and the value type. So the key type we're going to search for, and the value is going to store what's stored associated with that key. If I say people, Bob equals 13, what happens is this string Bob is going to be passed into this operator bracket function. So you have to overload this bracket operator to implement this insert and find. So what happens is that that key, that parameter, is going to contain the string Bob. So the first thing we do is we pass that string Bob into a hash function. That hash function behaves like a search. It'll tell us where is Bob going to be in my table. My hash function is very simple that I have set up. Let's see, where is the hash function defined explicitly? There it is. So the hash function is going to be just taking the first character of this string, minus it by character A, and then mod it by table size. Modding by table size will allow us to not go beyond the bounds. So I'm going to go ahead, pass Bob into this hash function, and then for Bob, it returns the value 1, because B minus A is going to give us the value 1. Mod it by 10 will give us 1, because table size is 10. So index 1 was where Bob has to go. And originally, this index 1 was blank, so we created the entry right there for Bob. That's all we had to do. Same thing for Dan. I went ahead and with the people Dan, I take the string Dan and first pass it into my hash function. And for hash function, you pass in Dan, the hash function will take the first letter of Dan, so D, minus A, it'll give us the result 3. If you do ASCII subtraction, it'll give us 3. Mod by 10 will give us 3. So Dan has to be an index 3. So we're going to look for index 3 in our table. And originally it was blank, so it makes the entry for Dan, returns the value field. Now, for the operator bracket function, it returns this value, this T2, by reference. So T2 ampersand, which means that it will allow us to update that value field in main. So what happens is, when I find the struct, or this, how should I call this, this node, when I find a node with a matching key, it returns this value field. But it returns it by reference, which means that it returns the address of that value to main. So here in main, I'm actually, this value field right here, that V field is going to replace all of this basically. The same thing as just setting 10 to that value field right there in my node. Because I return that value by reference, I can assign to that value in main. I return the address of that value field of that node. So allow me to update this to value 10. Let's go ahead and do some more examples with this. So it's kind of, conceptually it's not too hard to follow this, but it's, the coding wise can be a little bit of a challenge. And of course, items, I made a mistake here. So items is supposed to be 1, then 2. So every time we add a new element into our structure, we increment this items counter by 1, which means that we've added a new item into our table. So it's actually more of an issue we do open addressing, but for now, let's go ahead and just also apply it over here as well. So now let's go ahead and do some more work. So I'm going to go ahead and I'm going to try Vicky. Fairly Odd Parents, Icky Vicky. Team Easily Evil Babysitter Vicky. So I'm going to try Vicky. I'm going to assign Vicky the value 17. So the first step is that string Vicky is passed into that bracket operator. So this parameter key is going to contain the string Vicky. I would take that string Vicky and pass that into my hash function. The hash function does, so for our hash function, it's a very simple one. It takes the first letter, which is V, minus it by A, gives us the value 21. If we do this, I have this sort of table on my other screen here, so I know exactly what the value is, but it's really going to be just 21 is the result. And then we mod it by 10 to give us the value 1. So the table has a length of 10. We modify table length because the hash function could spit out some index bigger than the table size. And if we do that, we're going to go beyond the bounds of our table. And if we're lucky, it will cyc fault. If not, it will do something very, very bizarre. So we modify table size to make sure we don't go beyond the bounds of our table, because v minus a gives us 21, and we don't have index 21 in this table. So modding by 10 will give us the value 1. So what happens is we go to index 1 in our table, and our index 1, we have a node right there, but the key contains Bob. So we have a collision because Vicky and Bob both mapped to index 1 in this table. So index 1 contains Bob, so you have to keep on searching. Maybe Vicky is somewhere in that linked list. But right there we can see that there's nothing after Bob, so we hit a null. That means Vicky is not in this structure. So we have to create the node for Vicky. So I'm going to make a box over here. Have this point to that. And the key field, well, I'll just assign Vicky to it. So you just have to store that. So the key passed into this operator bracket function, you take that and assign that to that node's key field. And the value will be set to 0 because you're going to assign some default, and the default for integers will be 0. And then return. You return, so that node that contains Vicky, return that value field. You have a pointer probably pointing to this node, right? You're going to have some pointer, let's say I, pointing to this. So return I arrow value. So we return that value, and since the return type is type T2 ampersand, it returns that value by reference, which means that we'll be able to assign 17 to it outside of the class scope somewhere in main in this case. When I say equals 17, it assigns 17 because we returned value by reference. Well, I guess it's kind of hard to guarantee if you can make a hash function that makes no collisions because you don't really know where your keys are going to be. We could use statistics and sort of have kind of have expected results where statistically, if the keys are distributed in this type of distribution and its hash function is a very low probability of having collisions. So you could do statistics like that to kind of have a case where kind of assume a distribution of your keys. You have some either it could be a Boston distribution, some distribution you can have of your keys, and using that distribution, you can kind of try to create a hash function which will be a very low probability of having collisions. You could do that. There's a lot of advanced work right there, but of course, you could have a good hash function assuming some distribution of your keys that are to be inserted into your table. It's probably the best answer I can give with that. It sounds actually pretty sophisticated, distribution and all that. It's a very sophisticated term, I guess. I have to learn statistics on my own as well, my own personal research in the future. So I'll be learning that probably over winter break, most likely. So anyway, let's go ahead now. And I'm going to just continue with this. I'm going to say people. Let's see what else I can think of. I'll think of Larry equals, actually I'm supposed to have updated this items counted by 1 earlier. My mistakes, I keep forgetting that. But when we insert new elements into our structure, we increment items counted by 1 to denote how many elements you've so far stored in our table. So always have to make sure you do that if you insert a new element into your table. Say people, I'm going to say people Dan plus, oh, I'm going to have to apply this plus people Vicky. Let's go ahead and work this one out. But first, we have to find where is Dan in our table. So as always, we call the bracket operator, we pass in a string Dan into this function, and we're going to pass that string Dan into the hash function. Hash function will spit out 3. Every time I pass in Dan, it will run the same hash function every single time. It will take the first letter D, minus it by A, to give me the value 3. Modded by 10 will be 3. So Dan has to be index 3 somewhere in this table. So we go to index 3, and the first node right there, the key does match Dan. First element in our table, it does match perfectly, which means, okay, we found Dan. So return the value field. So return 10. That's the value associated with Dan. And then I want to go ahead and find Vicky next. So I have to, again, go ahead and have people, Vicky, I'm passing Vicky into that bracket operator. I have to pass Vicky into the hash function internally inside this bracket operator, and it's going to return index 1 again, because same idea, we pass in Vicky, so the first letter, so our hash function is first letter, V, minus A, will give me the value 21, modified by 10 will give me 1. So it will return 1. So we know Vicky has to be index 1 in our table. So we go to index 1. The first node's key contains Bob. That's not Vicky. So you have to go to the next element and keep searching that linked list until either we find Vicky or until you find a blank, or find a null pointer, sorry. If a null is found, that means we know we did not find Vicky. But if we find Vicky at that point, then return that value field at that moment immediately. So I traverse that linked list. The next node in our linked list, at index 1, next node contains the string Vicky. So I have a match. I found a node whose key matches the key passed into this bracket operator. So I found Vicky at this position in my linked list, so return the value field of Vicky. So I add these two up, I get 10 plus 27, or sorry, 10 plus 17, which gives me 27. I have to store 27 into wherever Larry is in my table. Well, let's go ahead and find Larry. So we have to take the string Larry, we pass it into my hash function, and for Larry, it's going to be the first letter L minus A will give me 11. Modified 10 will give me 1. So Larry has to be somewhere index 1 in my table. So what happens now, I go with my index 1, I first check the first character, the first node's key is Bob. That's not Larry. The next one is Vicky. That's not Larry. And next element is a null, which means, okay, we know that Larry is not in our table. So of course we have to create the entry for Larry. It's my key. I'll assign Larry to that. V is going to be initially 0. Increment items counted by 1 because I did in fact insert a new element into my structure. So I found an existing element, then don't increment that counter by 1. Otherwise, increment that counter by 1 if it's a new element you have to insert. So I create Larry, return the value field by reference. So then I say people Larry equals, it's going to assign Larry's value field to be 27 because returning 27 return that value by reference. So that way it'll allow us to reassign it if we wanted to. We can also just simply look at that value. We also can reassign it as well because we're returning it by reference. So that's all it really is to this chaining method. You just have to use hash function. It maps you to an index. You have to traverse that linked list to find that key. If you don't find it there, if you hit a null pointer, that means it was not there. Then create the entry on the fly and return that new entry's value field back to wherever you call this function. So either in main or somewhere else where this was called, it's going to return that value back to that function that called this bracket operator. So of course, I'll do more examples with other sorts of methods of hashing, but that's our simple one, chaining. So any questions on that before I go ahead and do some sort of analysis on this? So these notes are kind of, I'm going to use lines for my for this one note on my next file because I think this is a little bit kind of sloppily written, but really this one is going to be not the hard one. So conceptually, this is the simplest one to actually work out. So let's go ahead and just finish this up, and I can go ahead and go over the other sorts of hashing methods. So I guess sort of properties of separate chaining. So I'm going to use plus and minus to denote positives and negatives. So the plus here means it's going to be a positive. So a benefit of using separate chaining is that it's really an easy structure to maintain. Answer your question in a second. Easy structure. Maintain. At least conceptually, it's simple to maintain. See the question here. Yeah, so I'll go over resizing later on, but yes, if you were to resize or expand this table, you'd have to remap all of these into a different table because now the bigger table, the table size is larger, which means its hash function will be a little different because the table size value will be a bigger number. So technically, these keys have to go somewhere else in a bigger table. So you have to literally rehash everything in this table into a bigger table. For a binary tree instead of a second list. Let's see. I guess a binary tree would sort of guarantee that. So anyway, so yeah, so that's the idea with that. Anyway, so let's go ahead and I'll write some more properties here. And the other one is that because it's easy to handle collisions, because there's nothing to it. You just sort of insert a node into that linked list. So in this case over here, in our table, Bob, Vicky, and Larry are all going to cause collisions because all of them have the hash index 1. The hash function for Bob, Vicky, and Larry all returned 1. So we had multiple keys with the same index. So we had collisions right here, actually. But for collisions, it's simple to handle. We just insert a node to the end of that linked list, and that's it. So it's a very simple way of handling it. But of course, in life, if something is easy, it's not always the best idea all the time. That's, of course, the paradox, not paradox, but sort of the crutch of life. If it's easy, it might not be the best idea. Well, not always, but usually that's always the case. Usually that's the scenario where if it's too easy, then there's going to be problems with it. So the problem here is that, well, a negative is that not many ways to handle collisions, which is not really good. I mean, okay, it's easy to handle it, but if you have not many ways to handle collisions, then the problem is that um, you want to have different choices or ways you can handle collisions. That way you can try to spread apart your entries in your table. It's not many ways to handle collisions. It's kind of bad. I mean, it's easy to handle it, but then it's not good to have that scenario because clustering is very likely. Because you could, if you have collisions, then all of those keys will all be in the same place in our table. If that happens, that's very bad because now the probability of having collisions are high and the runtime will take a big hit if you have a collision. So, for example, what if, let's say, every single key we insert into this table all happens to be at index 1? The runtime is going to be O of n in that case, right? So basically, we just did all this complicated work just to be able to do linear search. I mean, that's pretty cool, right? We did all that hash table, this, and array of linked list, that, and all this cool stuff just so we can do linear search. I mean, that's pretty nifty, I think, right? I mean, that's cool how we can do linear search in a very complicated way like that. So the idea is that that's a possibility and that's not good. So clustering is always bad. Because clustering means the probability of having a collision is going to increase. So, you can already can see right there that this method, it can be a problem. So ideally, the search time is supposed to be a constant. O of 1 is the ideal result. Now, I don't have memorized the actual runtime for this, but I know for hashing, typically load factor plays a role in the runtime because statistically expected results, if this load factor is large, then the runtime on average is supposed to go up. So I think if you look at geeks4geeks.com, the offensive website, it has chaining. It does give you the runtime as it uses load factor as a factor to the runtime, but basically it's because as it increases, the expected runtime is supposed to kind of go up. But for us, we'll just go ahead and consider hashing as a very simple runtime. Ideally, it's constant if everything is all nice. Otherwise, worst case, it's going to be linear if everything's all grouped in one element in our table. And also having clustering is also bad because, well, it's going to cause future collisions. It's almost like, you don't want to have having a cluster in your table is like having one big target in your table that's going to be a very high probability of having future collisions. So clustering, okay, I got to turn off Discord right away because I don't want to see what's going on here during class. Turn that off. So, yes, clustering is a possibility. Clustering is always bad. So that's kind of the problem with chaining. It's simple to implement, but not the best strategy. Of course, you can hybrid and modify chaining to be a little bit chaining in other methods, but just pure chaining by itself, though, is not the best idea. But of course, you can mix and match with hashing accordingly. So let's go ahead now and go into our next sort of method. So this is, right now, we're going over methods of how to maintain a hash table and how to handle collisions. So separate chaining was one method. Let's go over another method right now. Go into open addressing. I'm going to go and actually linear probing. Let me go ahead and let me just describe open addressing first, and I'm going to make some subsections here for. So open addressing is kind of a class, a set of different ways to handle collisions. I'm going to go ahead and put lines over here. I always forget to do that, but this actually will make the note writing a lot better. So I should have done this a long time ago, but I keep on forgetting about it as I get too into the material in class, and I kind of forget to put lines there. So anyway, open addressing, what's going to happen with open addressing is we sort of remap the keys when a collision occurs. So unlike with chaining, we don't remap. We just sort of link all those nodes together for all those keys that had a collision. It's all we did for chaining. But open addressing, we're going to remap it somewhere else when a collision occurs. So I'm not going to go over all the technical details of the actual how the class would look like, but the same idea though. We're going to have a table size. So let's go ahead and just do a little, let's talk about sort of the class structure, just a brief sort of, I'm not going to write the entire thing out, but class structure, well, of course, you're going to have an items field, table size field. You're going to have all of that still. You can't get away from that. You're going to have your hash function, of course. So T2 ampersand, not hash function, your operator bracket. But a hash function as well, though. And T1, I'll call this key, I suppose. Have to have that, of course. You're going to have a struct table item, which is going to contain these two things, T1 key and T2 value. And we'll not have a pointer inside this because it's not going to be a linked list structure. So it's going to be just a straight regular array. So it's going to be an array of structs, basically. So your table it's going to be, sorry, I should write this a little nicer. It's going to be table item star table. It's going to be set to new table item table size. So your constructor will just set table size to some value. And you're going to, this table is going to be your array. And each element of your array is going to contain two things, the key and value. So it's going to be a struct array, basically. The hash function we're going to have as always. And for the lesson, we're going to be covering with hash tables. Will be the same hash function we're going to use. So it's going to be always a string, the first character, minus it by a, multiplied by table size. We'll keep using that approach just because it's a simple enough hash function. So for your assignment 7, when you create your own custom hash map, you may have a different hash function, but it won't be any more complicated than this method, except I just chose this one as a very simple one to actually use, simple for for teaching purposes. But for the assignment 7, though, it'll be something different, but not much harder than this. So similar in difficulty. We have to add up all the ASCII characters and then modify table size. That's not a hard one to implement, but it's hard to, in class, be able to, like, beforehand, compute every single possible key's hash value. So that's why I use the first letter minus A, because simple to actually in class just sort of, talk about this. So anyway, that's our structure as always. So we're going to go ahead now and go specifically into linear probing, which is a specific instance of open addressing. Linear probing. Let's put a line over here. Linear probing. So we always maintain a collision counter. So for every insertion, or for every time, so every time, I'll put it differently, every time we use the bracket operator, we set some collision counter to 0. We will call this collision counter as I, because I is our default sort of kind of that sort of counter is always I for some reason. So we'll call it I. Linear probing, how it's going to work is the following. So after every collision, so we increment I by 1 and remap key to index whatever the hash function returned. So I guess the hash function passed in the key plus I modify table size. So if a collision happens, increment I by 1, and then the same hash function, same hash index you used earlier, use the same index you're going to use, and then plus I modify table size. So layman's terms, what's going to happen is when a collision happens, try next elements in your table. For the collision, try next elements in your table until finally either you find the entry in your table or you find a vacant spot to insert this key into. That's really all there is to linear probing. Of course, let's go ahead and do an example just so we can try to understand this, but that's really all there is to it. And in fact, the other ones will be just as difficult as this, but let's go ahead and just talk about, how to implement linear probing, of course. So I'm going to, once again, right below, I'm going to have my int main. And I'm going to define some hash objects. So I believe hash map is what I always use for my custom hash map type. So hash map. And again, we'll have a string be our key type and int be our value type, as always. And I'll call it people again, sure. All right. Let me go ahead and zoom out so we can sort of write some more stuff here. I'm going to create a table right next to this. I'm going to use a shape here. And I'm going to allocate a table. Let's see, maybe I should make it sort of 10 elements. So that way it's easier. I'll make it 10 elements. So let me just make sure I can count this correctly. 2, 7, 8, 10. Having lines there is really nice, actually. It makes it a lot easier to just put it next to this. I'll make this green. So let's distinguish that. Okay. So we're going to have the following. So I'm going to actually assign indices here. I'll use red as indices. I don't want to put the array brackets because it takes so long for some reason to do that. So this will be the array brackets. And every entry will have a key and value. So I'm going to use K and V just to shorten this. So K and V. I'll write this manually. Copy and pasting this will take longer for some reasons. It won't copy correctly. I'm going to be fiddling with that for a long time. This is actually fast if I just go ahead and just write the key and be like that. So every entry of this table, which is going to be stored inside this people object, is going to be a struct array. So each element in this array contains two things, a key and value, basically. See if I can sort of move this over slightly. So there we are. Space for that. So this will be our table. So if we go up to our class structure, this will be our table. And it contains new table items. So we're going to have table size will be 10 in this particular instance. And each element is going to be a table item object. So it has two fields, key and value for every entry. So table size will be 10. Items will be 0. Go ahead and put this below here. So we're going to have items is going to contain 0. Then table size will just be 10. Okay. So let's go ahead and insert some elements into this structure. So I'm going to first say people. And let me see if I can think of, let's have Mary. Let's have Mary will be 16. Okay, so you have to go ahead and look up Mary in our table. So as always, just like for the other method, for the chain method, we have to first, we pass Mary into the hash function. Our hash function is very simple. The first letter, M, minus A, will give us the value 12. Multiplied by 10 will give us index 2. So index 2 in our table, we can see here index 2 is a blank. Now, of course, every entry in this table, we're going to set the key and value to some default values. So within our class, we have T1 and T2. So I would have to literally just do the follow. I'll put this here really fast. I'm going to erase it in a second, but you'd have essentially table index 0, let's say, dot key would be just T1. And then table index 0 dot value would be this. That's how you store default values into your structure. So T1 and T2, whatever type they are, is going to assign some default values. So if T1 and T2 are sort of primitive types, it will just work no problem. If T1 and T2 are custom types, it's going to call that object's default constructor to set some default value to the key or value. So you have to loop through your table in your constructor to set every element to be this. And this is going to be just that default value for whatever T1 and T2 are. So if T2 is integer, that T2 then left right parentheses is going to return 0. It's going to store 0 into the value field. If T2 is a custom type, it would have to use the default constructor of that custom type to assign a default to the value field. So you have to do this. So if let's say if the key contains, if let's say the key in this index contains this value, that means it's a blank field. There's nothing there, basically. How we can think about that. I'm going to erase this because I want to have room to actually examples, but of course on the assignment 7, I'll go over this as well in the handout, and I might make a video probably for it because I may not have time in class to cover the assignments. May have to do a video that would just sort of go over all that. It's probably better if I make a video because it's nice pre-made video that I can kind of, stop at certain spots to make sure I don't make a mistake on anything. So I think it's probably better anyway. But anyway, let's go ahead and just go into this example. So Mary goes to index 2. Index 2 contains nothing. So we're going to write Mary over here. We're going to write Mary, which means that this entry now contains Mary. And the value, well, it's going to be already 0 anyway. So maybe I'll put zeros here for all of these actually, just to be sort of more consistent. So they're all going to be 0 initially. Every entry in this table, we assign the key and value to some default value. And since integers are the value fields, then all these will be 0 for right now. So we store Mary into that position, and then we're going to return that field. Return a value field for that index where Mary resides. Return value, and as always, it returns value by reference, which means that it'll be able to assign 16 to the value field outside the scope of the class because we return the address of where that value is going to be stored in our hash table. So that way it knows when it says equals 16, it knows to store 16 into that value because it returns a value by reference. It's going to assign 16 to this value field for Mary. Okay, so that seemed to be kind of all right so far. So let's go ahead and insert more names into this structure. I'm going to try the letter Y. I can't think, let's try Yasmin. I think that starts with a Y. I've seen that name, Yasmin. Let's try Yasmin. So you want to go ahead and find Yasmin. I'm going to assign 24. So again, we have to go ahead and look up where is Yasmin in my table. So again, we go ahead and pass in that string, Yasmin, and we're going to look at the first letter Y. So we're going to pass that string into our hash function. Hash function will go ahead and check the first letter, which is Y, minus it by A, which will give us the value 24. Mod it by 10 will give us 4. So Yasmin has to be index 4 in our table. Index 4 is blank. So we're going to go ahead and write Yasmin there. I should have done this earlier, but item's supposed to be 1. And now we're going to insert Yasmin into our table, index 4, and increment our items counter by 1 again, because on a new entry that was inserted, we increment a counter by 1. We always want to know our load factor because if the items over table size gets very large, we have to resize our table. Because our table is very full, then the probability of having a collision is very high. So having a very empty table gives you a sort of an expected sort of, it's going to make it so the probability of having a collision is low if you have a very empty table. So we want to know if it's getting very full, we have to think about resizing. We're not going to resize anything just yet. We'll worry about that probably next week. But anyway, it's not hard conceptually. It's just hard to code that, of course, to resize a table. So anyway, return the value field of Yasmin as by reference, and we're going to assign 24 into it in main, I guess. Like that. So now let's go ahead and have some cases now where we're going to have some collisions. So I'm going to go ahead now and just say people. Let's see what we have here. Trying to think of a name that's going to cause the collision, or let's see. So I'll try Ed. So people Ed, and we're going to assign it to be just maybe people Mary. Plus 5. So let's do an example like this. So here, what's going to happen is I'm going to first look up Mary in my table. So again, we take this Mary string, it's passed into the bracket operator, and we pass Mary into the hash function, as always. And the hash function takes the first letter for Mary, so M, minus it by A, will give me 12. Oh, wait, it's supposed to be 12. Oh, supposed to be up here, Mary. My apologies. Okay, that's fine. It's supposed to be next to, I don't know why did I put it at 3? It's okay. It's supposed to be index 2 because Mary, m minus a is 12. Multiplied by 10 is 2. So I apologize for that. So it's supposed to be index 2. I don't know how in the heck I put it up at 3, but that's fine. So what happens now is, okay, we're going to go ahead. It's not going to cause a collision, but it's okay. I'll make another example in a second. So you first look up Mary. So we use our hash function. It returns 2. So jump to index 2, and we index 2, we see that the key does contain Mary. So we found an existing name in our structure. So that means, okay, return the value field. And we don't have to increment our count by 1 because we found an existing key in our table because Mary was already there. We didn't have to create the entry for Mary because we know that index 2 is where Mary has to go. We jumped to index 2, and that key in that index in our table contained Mary. So we know that Mary has to be there. So we go ahead and take that 16 plus 5 will give us 21. I'm going to assign ed the value 21. I have to first find ed in my table. So, okay, so ed, I pass in the string ed into my bracket operator, and then I go ahead and pass ed into the hash function. Hash function takes the string ed, which contains the first letter is E, minus A is going to give me 4. Modified by 10 is going to give me 4. So it's going to basically jump to the next 4. We see that, well, 4 contains Yasmin. So that means Ed can go over there. Yasmin already took up that spot in our table. Okay, so fine. What's going to happen now is for linear probing, we're going to try element at hash table plus 1 modified by table size. Because what's going to happen is we have our counter I. We had one collision, increment countered by 1. So it's going to be the hash value of ed, which was 4 plus 1, 5 modified by 10. So all we're going to do is try next element in our table. Next element is vacant spot. So we're going to go ahead and write ed right over here, increment the counter by 1, and then return that value field at that index where we found or created ed. We return value. Yeah, so in the worst cases, this would be O of n if you have a lot of collisions. So, but right now though, it's fast because we won't have too many collisions so far. But ideally, every hash is always going to be constant. But in the worst case, it can be very bad. But there are ways to avoid that worst case, I suppose. But this could be worst case O of n once again. So let's see, if we have to resize the table, would the indices of all the values have to be reshuffled since we're modifying? Yes. So if we were to resize this table, then we'd have to remap Mary, Yasmin, Ed to a different position possibly because what happens is table size would be a bigger number. So for example, let's say for Mary, it was going to be m minus a, so 12 if I take the first letter m minus a, it would give me the value 12. If the table has 15, it would be 12 mod 15. So index 12 is where Mary would go, not index 2 anymore. So you have to remap everything in your table into a different position in your hash structure. So you have to remap everything basically. Yeah, because table size modifies, so hash function is going to be a little bit modified as well to remap everything, which is, I mean, it's actually conceptually simple. It's also the code for it is simple, so I might even give you guys, I gave the code last semester for the students how to remap because it can be, I used the this pointer in a few spots to make it very simple to redo it all, but anyway, we'll see. But anyway, it's simple conceptually, but of course it's challenging to actually code this because it's always harder to code stuff, unfortunately. So Yeah, that's we have an agreement on that. So yeah, and that's yeah, that's we definitely can agree on that as well. So now we're going to have 16 plus 5, 21, and we're going to assign Ed the value to be 21. Now I'm going to try to cause some chaos, but not just quite yet though. So I'm going to do one more, see what else I can do over here. Okay, so I'm going to go ahead and add one more name here, and then have some chaos. So let's go ahead and add Xerxes, which is, I think, from 300. I'm not going to use Spartacus. Oh no, I think it was Leonidas. So Leonidas was like the main guy, but I think Spartacus is famous in Sparta. But anyway, Xerxes. So we're going to assign Xerxes. And we're going to, of course, maybe just take people Yasmin just to sort of some extra work here involving the hashing. I'm going to assign plus 6. So you first have to look up where's Yasmin in my table. So you go ahead and use the string Yasmin. You pass it into our bracket operator, and we're going to pass it into our hash function. So then our hash function takes the first letter Y, minus it by A, will give me 24, mod by 10 will give me 4. So index 4 in our table contains the string Yasmin for the key, so we found Yasmin. So we go ahead and return the value 24. Plus 6 will be 30. We're going to assign 30 to Xerxes. We got to find Xerxes in our table. So Xerxes, we pass in that name into our bracket operator. Then within the bracket operator function, we pass that into our hash function. So x minus a gives us 23. Multiplied by 10 will give us 3. Index 3 is blank. So we know that Xerxes has not been inserted into our table yet. So blank means that we have not inserted Xerxes. Either index 3 has to contain Xerxes or something else in order for us to keep on searching. But since it's a blank spot, we know that Xerxes could not have been inserted into our table just yet. And then return the value field. So we found index 3 is where Xerxes has to go. Return that element's value field by reference. So that way in main, I can assign 30 to this field. Now at this point, in theory, you'd want to actually resize your table at this point now, because now we're 40% full. We have a pretty high probability of having a collision. And also look at this, we have 2, 3, 4, and 5 contain keys. So we have a clustering going on here as well. So we have a few problems now. So it's not a very good situation to be in. But I'm trying to show you, what the worst case can happen with linear probing. But this is already a very bad spot to be in terms of hashing. But let's just go ahead and just work with this some more. I'm going to try the next name. I'm going to use Wayne. Wayne's World. Party on Wayne, party on Garth. Anybody know Wayne's World at all? Sorry about that very cringy line from Wayne's World. It was a cool movie back in the 1990s. It was a fun movie. But you guys probably don't remember that. You guys are young to remember Wayne's World. All right, that's good. We got one person at least. It was an awesome movie, Wayne's World. It was a great movie. At that time, it had all that sort of satire of like cultural, social satire and everything like that. It was really that movie that started all that, at least. So anyway, we're gonna go ahead and insert Wayne, and let's see. I'm gonna go ahead and just you know just do some more lookup just to kind of practice hashing. Please marry plus 7. Sure. So we're going to go ahead and first look up Mary in our table. So we go ahead and pass in our hash our string Mary into a bracket operator. We'll first look at our first letter Mary. The first letter minus the hash function takes first letter M minus A to give us 12. Multiplied by 10 will give us 2, not 3. For some reason, it's going to be 2. And index 2, we see that index 2 contains the key Mary. So we found Mary, so return the value 16. Return a value field for that element. And plus 7 is 23. So I gotta go ahead and find Wayne in my table. So Wayne, we pass Wayne into our bracket operator, and we're going to pass Wayne to our hash function. Our hash function just takes the first letter of Wayne, which is W, minus it by A, will give me 22. modded by 10 will give me 2. So it's going to map Wayne to index 2. Okay, index 2 contains Mary. That's not Wayne. So we have a collision because we had something else that had the same hash value. Okay, fine. So what we're going to do now is have our collision counter I become 1. So we take the Wayne's hash value 2 plus 1 modified by 10 will be 3. Index 3, well, that contains Xerxes. Another collision happened. Okay, fine. So we're going to take I incremented by 1, so our collision counter will now be 2. So Wayne, which has the hash value 2, plus 2, the collision counter, because remember, we keep on incrementing this I by 1 every single time. So it's going to be hash function 2 plus 2 is 4, modified by table size will give us 4. We have Yasmin there. So again, we found a collision, so fine. Increment I by 1 once more, so I becomes 3 now. So our hash value is going to be 2 plus 3 modified by table size will be 5. That contains Ed. So again, we have a collision, so darn it. Let's increment I once more. So let's increment I to make it 4. So Wayne's hash value was 2 plus I, which is 4, will give us 6. Modified by 10 will be 6. Index 6 is going to be blank. So you finally found Wayne's spot. This is a blank, so we have to go ahead and increment our counter by 1 because we have to make a new entry for Wayne. So I'm going to insert Wayne right there into index 6. Return value of Wayne. So it returns the value by reference, which will allow us in main to reassign that value to be 23. So that's, the idea for how it's going to actually work. Let's just do one more example just to sort of show you some more content here. So I'm going to let's go ahead and add one more name. People, I guess I'll use Ada from Resident Evil. Ada will just be yes. So for open addressing, the benefit is that linear probing is a very simple approach, but you can do all kinds of complicated methods of remapping. So the benefit of using open addressing over chaining is you have more options for remapping on collisions. So linear probing is a very basic method, but double hashing is the more preferred way, and you can actually remap and spread your keys apart. So there's more options you have with remapping on collisions is the real benefit of open addressing over chaining. Minus. Yep, you got it. So let's do this last example. So I'll go ahead and first I have to look for where to Wayne in my table. And it's going to be another tedious process again because we're going to first go ahead and we're passing the string Wayne. First letter of Wayne is going to be W, so we're going to use a hash function to map Wayne. So W minus A is going to give us the value 22. Modified by 10 gives us 2. What's going to happen is, just to kind of speed this up, it will look at index 2. Doesn't contain Wayne, so it's going to try next element. Linear probing just tries the I counter increments by 1, so it's going to constantly just move down the line, basically. So index 3 is not going to contain Wayne. Here is index 4. Here is index 5. And finally 6, this index contains Wayne. So this I counter increments by 1 every single time to try the next element in our hash table until finally either we find our name looking for the refined name Wayne, or until we find a vacant spot. A blank spot means that we have not inserted the element yet. In this case, however, index 6, we finally find that index contains the key Wayne. So we found Wayne, so return 23, return the value field associated with Wayne, like that. And then, we got to go look for Ada. So, okay, so we first pass an Ada into our bracket operator. The first letter is 8 minus A will be 0. 0 mod 10 will be 0. index 0 contains a blank. So we're going to increment our items counter by 1. We're going to write eta into this position, return the value field of that item by reference as always, and it will be able to assign the value. So 23 minus 4, 19 will be assigned into eta's value field. So that's kind of how it works. Let's take a look. See a question there. Oh, sure. Let's go ahead and try people STE. Okay, so let's try that. So, so question here on the chat is the following lookup. Let's go ahead and try this one out. So STE equals people Mary plus people Jasmine. Let's go ahead and try this out, see what it gives us. So we first have to look for Mary in our table, as always. So I'm going to go ahead and just say, well, I pass Mary to my hash function, and it's going to return index 2. So it's going to go through m minus a, which is going to give us 12 multiplied by 10. Index 2 will be where Mary has to go. Index 2 contains a key Mary, so we found Mary just like that. So that was successful. Return 16, which is the value associated with Mary. And then for people Yasmin, we have to go ahead and look up Yasmin in our table. So you have to take the Yasmin string, pass it into the bracket operator, and then we're going to look at the first letter Y, minus it by A, would give us 24, multiplied by 10 would give us 4. Index 4 does contain the string Yasmin, so we found Yasmin right away. We return 24, and this sum will give us 40, I believe. We're going to assign 40 into the string STE. Let's go ahead and look up where is going to be STE in our table. So we're going to first pass an STE to the bracket operator function. And what happens, the first letter of S is going to be, STE is going to be S. S minus the letter A is going to give us the value 18. Multiplied by 10 will give us 8. So jumping to index 8 in our table, index 8 is going to be a blank entry, which means we have not inserted his name just yet. So I'm going to insert this name right here, increment this counter by 1, and return the value field of that entry by reference. So it's going to allow us to assign 40 into it in main like that. So that's how that would work. Any other questions or requests for any other entry to be inserted? Okay, so that's all right, so it looks like we're kind of okay. So this table is actually now really a bad situation because we have a very full table now. So probability of having a collision is really, statistically, it's 70% probability of having a collision, which is pretty high. So when that happens, then you can expect linear probing to do a lot of work. So in the worst case, again, you can see that it's going to take up, it could be O of n time to find something if you have a lot of elements. And also the problem with linear probing is that, again, it's a simple method of remapping, but simple, again, might not be the best idea because now the problem is if a hash function returns 2, 3, 4, 5, or 6, all of them will cause a collision. So a lot of clustering is a problem because then the probability of having a collision is high because if you're spread out a little bit at least, then maybe we could have a case where there's no collision. But now indices 2 through 6, so any hash function returns 2 through 6, they'll all cause a collision. So clustering is kind of a bad scenario because it gives a high probability of having a collision in that case. Say, so if you were to add two values that previously collided, we need two counters then, right? Well, I guess for every single instance, you would have its own separate counter. So this I counter would be a local variable defined inside the bracket operator. So every time we do this, it's going to be a separate sort of instance. So when I go ahead, say for example, if let's say I'll just do one more example, just right here, just one more. I'm going to say people um, Ed equals people Wayne. Let's just say this is not going to insert anything new into our table. So we're going to first look for Wayne. So Wayne, it gives us index 2. So index 2 does not have a Wayne, so you have to increment I by 1, try next element, next element, next element, and next element, and we find a Wayne right there, the value 23. You have to go ahead and look up Ed. So Ed has index value 4. If I pass Ed into my hash function, it returns 4. Index 4 has Yasmin, so then we're going to increment I, so I will be 0 in this case, increment I by 1, so then 4 plus 1 is 5, Ed's right there. And we're going to assign Ed to be 23. So every time we do a new lookup, the counter is reset to 0 every single time for each lookup. Is the idea. Yeah, because it's its own instance of this. So we call a function, it's a different instance for this function for its own parameters. So you can just declare I locally in that bracket operator and set it to 0. So that way it's going to always start off at 0 for every time we use the bracket operator. So, yep, you got it. So that's basically linear probing, a very simple way to remap elements, but again, it's not the best sort of approach. So I'm going to go ahead and sort of define all of these later on, but for now I'm going to just kind of begin the next sort of probing method. But I'll go ahead and I'll sort of define their, do some notes on their properties after I finish all of these. But let's go ahead and now cover our next one. So then we're going to have quadratic probing, the next sort of open addressing method. Quadratic probing. Now, I'm not going to actually, I'm not going to go through and create the entire class. It's all going to be exactly the same as linear probing. We have the same struct table item. Our table will be a one-dimensional array of table items. So it's all the same. So the contents, class, yeah, I know I have a class coming up at 10, don't remind me. It's a pretty fun class, the modular CS135. I actually enjoy that class. Actually, it's pretty neat actually. So class contents are the same as linear probing. So same content because it is, after all, open addressing. So they all have a very similar structure, except the difference really is how we remap a key to a new position when a collision happens. So quadratic probing is pretty simple. So we have a collision counter as always, I, and we're going to use hash function using our key plus I squared modded by table size. So same idea, except the difference now is not adding by I, but by I squared. And once again, we increment, so increment I by 1 after every collision. So same idea. The difference is instead of plus I is plus I squared. That's the only difference really with quadratic probing. So of course I'll do examples with this, but this is not going to be too bad. So I don't have to spend too much time, I don't think, because it's not going to be a lot different than linear probing. But the purpose of doing plus I squared is so that way, when collision happens, we try to spread apart the keys a little bit. So if you go to linear probing, I'm going to scroll up for a second here. If you had collisions, all it did was it took the element and put it to it sort of would linearly search and find a new vacant spot like that. But that method though is pretty simple, but the problem with that method is that we can have clustering happening in our table. Because the keys are not going to be remapped in a way where they'll be spread apart. They'll be kind of bunched together because our sort of remapping method's very, very primitive. So this one is a bit more sophisticated, and because of this, there's a good chance that the keys could be spread apart a little bit. Because having sort of our table, so the two things to really make sure we have sort of lower our chances of a collision, and no collisions increases runtime. One is to remap our elements, but try to spread them out still, and also having a very empty table. So quadratic probing is going to try to remap them and spread apart the keys a little bit. So that way we don't have that clustering, or we hope to not have that clustering. So this method is really not so difficult, but just a little bit extra because I guess maybe computing I squared can be a little bit harder, I guess. I don't know. That's probably why it's a little bit more tougher. But conceptually, though, it's not really that much harder in actual linear probing, but this can give us a more of a favorable result compared to linear probing. So I'll cover this and I'll cover the double hashing next week. And I'll go ahead and sort of put notes here for all of these. Also, we'll cover assignment 6 on class on Monday, which I'll have an assignment posted over the weekend sometime. But I guess that'll be it for today since we are almost out of time. So I guess take care, you guys. Stay safe. Thanks for watching. And I will see you guys next week.